This session is abusing performance optimization weaknesses to bypass ASLR, and your speaker is Byoungyoung Lee.
Thank you for the introduction, Ricky. And my name is Byoungyoung Lee, and I'm from Georgia Tech, and we have a bunch of the collaborators: Yeongjin, Jang, Tielei, Wang, Cheng Song, Long Lu, Taesu Kim, and Wang Lee. So here is some sort of the log system attack trends. So we always want to inject the code and execute it. So that sort of the code can be located in the stack, or that sort of the code can be located in the heap. And you can simply jump into that sort of the code. But the game has been changed a bit after having some sort of the production techniques like non-executable stack or ASLR, non-executable stack. So after doing this, so executing existing code out of original program order. So you can do the return to libc, or you can also jump into the gadget. People usually call it ROP. But in general, to launch this sort of the different attacks, the attacker needs to know the address of the stack or heap object or code gadgets. So you need to bypass ASLR anyway to do some attacks. So this is the ASLR, address space layout randomization. So this is actually implemented to introduce diversity into the memory layout of computer systems, and hoping that this can defeat the many easily replicated attacks, like simple return to stack or something like that. So here's the brief history. So ASLR is not really adopted at once, because implementing ASLR itself involves the computing powers. And so that's why, so there is some history. So first, the stack randomization has been introduced first, and then there is the PAX Prozac, and then Linux kernel mainstream eventually get this ASLR implementation in 2005. And after that, Microsoft Vista and also macOS X Leopard implemented the ASLR. And also after that, we also have a bunch of the mobile devices like iPhone or Android, and these mobile devices also started to implement the ASLR. So to bypass the ASLR, we usually did there was generally two different approaches to bypass the ASLR. The first one is about we can take the advantage of the non-randomized data structures. Like there was like executable compiled without the PI flag, which means that it is just not really supporting the ASLR for this specific module. So yes, because there's no ASLR, it is using the fixed address. So the other one is about the virtual alloc or map view of the file. And because since there was some implementation issues on Microsoft Windows, so this sort of the stuff were not really randomized. So yeah, if you know the address of these guys, so that address is always static. So you can take the advantage of it. And also there was another data structure called shared user data, and that was also located in this fixed address. So what I mean by here is that if the data structure or if some sort of the function is not really randomized, then you can just use that address. So the other sort of the attack is abusing the low entropy. So because you can, so especially on the web browsers, or if it is using JIT, then you can spray a lot of your code on the memory. So I think you are familiar with the heap spray, so you can just dump it out a lot of the code, and then hoping that you can, your overwritten address can point to this heap spray. So this is pretty popular and working pretty well. And also there is JIT-spring. And JIT-spring has some different issues, like you need to bypass constant folding or constant blinding, but it used to be working. And also, if the server is only using the fork only, so like if you're getting another connections, and then if you're simply doing the fork, then the address space is always the same for that specific session or for any future sessions. Then you can take the advantage of it. So we're going to talk a little bit more about this fork only servers in the Android part, but let me go over. So the other sort of the way to bypass ASLR is that you can exploit a lot of some vulnerabilities. Like if you can exploit this sort of the vulnerabilities like type confusions or heap overflow, use after free, integer overflow, format string, or uninitialized memory read, then there is a high chances that you can actually get some of the memory footprint, and that memory footprint usually have the address, like virtual function pointers. And usually if you have a virtual function pointer or a function pointer, then you can get the whole module address. But today we are going to talk about something different. This is not really about taking advantage of the non-randomized data structure, but not really about exploiting certain vulnerability. But we're going to talk about something performance-oriented designs that were us with ASLR. So this talk has two different parts. The first part, I'm going to talk about some script languages and how it is implemented hash table and how we can infer or read the key so that we can get the address. And the second part is about Android Zygote. So let me start with the first part. So before I actually talk about this, the script languages, first let me introduce the hash table. So hash table essentially maps the keys to the values. So pretty simple. I actually stole the picture from Wikipedia, and I hope this can really help, though it looks really a bit confusing. And keys are hashed to find the proper focus. And this is actually the key point of the design, hash table designs. So this computation can be done like this. So if you have a key, and given the key, you compute the hash, and then just take the mod on array size. So this is the reason why it is doing the mod operation on the array size. It's just because most of the hash tables are implemented with the underlying array table, and you want to make sure that that bucket index doesn't go beyond the size of the array. It's very, very simple, but here's some problem. So because the array size is pretty limited, there has to be always collisions. So what this collision means is that let's say from this, when you're computing this bucket index, and even if the key is different, so that bucket index can be the same because the array size is always limited. So people usually call open addressing. So people usually use open addressing to find the next available buckets. So there are generally three different techniques. First one is linear probing, and linear probing means that when you're searching the next available bucket, you simply do the linear fashion, like just do the +1, just search the next bucket. And quadratic probing is that when you're searching the next bucket, at the first time you try 1, and then you try 2, and then 4, 8, something like that. And double hashing is that instead of using the single hash function to find the next bucket, you can also use the double hashing so that you can make this searching order more unique or more different. So I talked about the hash table, but you may wonder how it is related to the ASLR. So let me talk about the built-in hash tables. So if we have a lot of the languages like JavaScript, Java, Python, Ruby, and all these different languages also implement the hash tables. Though Python call the hash table as a dictionary, but the underlying implementation is pretty much the same to the hash table. And sometimes they use memory addresses as a key for some certain object. So you may wonder what this means. So what is this? Memory addresses as a key. So when you're implementing these hash tables for general whole object in the dynamic languages, and you may want to get some unique identifier for some object. So you can, because if you're simply using the memory addresses as a key for this sort of the object, then you can really, the implementation can be really fast, and also it is very, very easy to implement because you can simply do the static casting or reinterpret casting in the C++. So absolutely, this can be implemented in some other different way. So the first one is that you can also use the random numbers every time you encounter some certain object, and if you want to assign the unique identifier, then you can just call the crypto function so that you can get your random numbers. But this is not really obvious sometimes, but because this key spaces, this key spaces is like sometimes 2 to the 16 or 2 to the 32. And it is possible that there can be the collision, even if it is the crypto hash functions, crypto random numbers. And yes, so that is always a problem. And if you're using the static counters, so like when you're assigning the unique identifier for the first object, you simply assign 0, and the next time you assign 1, 2, 3. Yeah, you can absolutely do that, but if you want to do this, then you need to consider the thread safe, because this is a multi-threading program, so you never know that the counters are actually, this is one of the counter value is used for different objects. So yeah. So as I mentioned, the key can be used as memory addresses. So the question is, can you actually read the key? But an answer is, if the language allows, yes. So if you're familiar with the Python, so you can simply create the general object with this x equals object. And if you get the ID of this object or trying to get the hash of this object, then it is simply returning most of the address bits. So it's not really surprising. So I think this is actually intended design for the Python. So because if you're running the script languages, then you can do almost everything. So it doesn't really matter whether you know the address or not. But let me tackle this a little bit more about how this can be a possible problems. So yes, usually running scripts from the shell means you have everything. So you can do, like in Python's case, you can import the OS and then call like os.system, and then you can put whatever you want. Then you don't even need a shellcode, so you can do whatever you want. But here's the question. What if it is actually running in the restricted environments? So like sandbox environments are really popular. And right now, many script languages have sandbox-like extensions, especially for clouds. So if you look around the cloud app engines or whatever, then sometimes they have the Python or Ruby shells. And many of them are actually implementing in-house J or sandboxing. So they get rid of most of the system functions, and also they restrict the file system accesses. So I would say it is not really supposed to suppose that you can get the address. But right now, many of their implementations are not really considering it. You can possibly, or we actually checked some of them, and they are actually returning the address. And because this sort of the heap addresses are pretty kind of unique for platform, and you can sometimes tell which operating system it is running. Maybe even this information itself is not really useful. There's getting to know the platform, but yes, so that address information can be also used for some sort of the OS fingerprinting. Yeah, so the other question is that maybe the language doesn't really allow to directly read the key. Then how can you read it? The answer is partially we can still read it via timing a text. So here's the whole table that we actually built, and we actually went through the different languages. So in the Python cases, and the Python, Ruby, Julia. Julia is like dedicated languages especially for the cloud environment. And all these three cases, we were able to read the key directly because there is interfaces, so we can get the address. But PHP is a little bit different, although you have interfaces to read the key, but the key that you actually read is not really the memory address. So we're going to talk a little bit more about this because this PHP's implementation is pretty unique and interesting. In Java's case, so there is two different virtual machines, largely. One is Java Virtual Machine, and the other one is DVM in Android. And Java VM cases, you can read the key, but that is not actually the memory address. It is just random value. But the interesting thing is that we actually went to the source code implementation of the JVM, and what we found is that they have some different options in the compile options. And if you specify some specific compile options, then you can choose to use the key to use the memory addresses as a key. But I don't know why this is not the default the compile options right now on JVM. But there is a the code spec which is exactly doing this. And DVM's cases, so yeah, can you read the key? Yes, and it is also the address in DVM's case. And JavaScript case, so if you think about the JavaScript, you cannot really read the key of the hash. So we need some way to infer the key. And for this WebKit and V8 cases, so WebKit is used for Safari, and V8 is used for Chrome. And in the WebKit's case, we can infer the key, and we can also, and that inferred key is also the memory address. And V8's cases, although you can infer the key, we were not, so that key was not the memory address. It was just still the random value. So here's how we read for different implementations of Python's cases. You can just create the object, and you can call the built-in ID functions or hash functions. And Ruby cases is also pretty much the same. You create the object and get the ID of the object. Yes, the ID is actually the address. In Java's cases, so you create the object, and if you call the hash code function, then you can get the address. So you may say that the Java, especially for the direct VM, because you can run the native code, so getting the memory address information by running the Java may not be that interesting or something. But in the future, it is possible that the Java also employs, DVM also employs the native client model, which is that the process is running the different process from the actual DVM. So it is possible because in these cases, they are relying on the different address spaces. So it is possible that this address information from the DVM side can be useful. And in the Julian's cases, so you can create the type object and then get the ID of the object. And it is the address. So for the WebKit cases, it gets a little bit complicated. So what we did is that we actually took the advantage of the name object. So this name object is adding a unique private properties to any object. And this was the new experimental features for ES6, so-called harmony. And so because the specification says this object has to be unique, so they were using the memory addresses. This is a simple implementation. I mean, this is code snippet that how that name object is actually implemented. And if you look at this part, it is simply doing the casting, static casting and reinterpret casting on this object, on this pointer. And this pointer is actually that name object. And then you can get the hash. So how do we actually infer the key? Because we cannot directly read the key. So how do we infer? So there is some requirements to actually infer the key. And the first one is that the collision resolution should follow a certain order. The second one is that the hash algorithm must be deterministic. And third one is that hash tables must be controllable. And this is all possible in WebKit cases. So because because it is using double hashing, double hashing is actually the deterministic. And also, so this hash algorithm is deterministic. And also, how to control the table, because instead of using the name object, we can also put the number or some other object like string. Then we can always get the hash, the key, the mapping between the key and the hash. So the problem becomes something like this. So you have one single hash table object, and you're gonna pull out, you're gonna dump a lot of the object, like number object or string object or name object. But here, the catch here is that the, for this number object or string object, you know the keys and hashes. But for this name object, you don't know the keys, and you don't know the hash either. And you cannot really read the key as well. So the whole question becomes that how do we actually read the key and hashes for this name object? So we need to understand to actually infer this, we need to understand how the hash function is working. How this collision resolution is working. So because double hashing is kind of a little bit complicated, so let me take the example from the linear proving. Linear proving, as I told you, is that when you are finding the next bucket, you simply do the +1. You simply try right next bucket. So in linear proving, if there is a collision, it is simply try the next block, next slot. So given the key k, and if it is ith trier, then what it is doing is that hash dk. This is hash onto the key, k, and then plus I. So it's just a +1. And then you mod on the table size. So let's say you want to insert, so let's say there is the hash table with the size 8. And then you want to insert this number object. By the way, let me simply assume that the key and the hash for the number object are still the same. Like if you put the 1, then the hash will be still 1. So if you do this, then if you take the mode 8, then the bucket index will be 1. So this bucket index number 1 will be filled up. And if you try next, if you try to insert this number 9, then it will compute the same, and it will be still the number 1, right? So what this doing is that it's going to try the bucket number 1 first, and then because it is filled up already, so it will fill up bucket number 2. And then if you, again, try to insert number 17 object, and then if you take the mod 8, then still the number is 1, so it will fill up bucket number 3. So how we actually going to attack is that we actually searching the timing differences. So let me assume that the table is filled up already, except the bucket number 0. So what we can do is doing some binary testing. So because the time difference because the search order is deterministic, so there is always worst case and best cases. And worst cases means that you're going to spend more time to search the empty bucket. And if it is best cases, it will simply return the result, so there will be less computation time. So let me show you this number 1, these cases. So let's say bucket number 0 is not filled up, and if you try to insert number 1 object, then the bucket index will be 1, and then number 1 first. So you will try here, and then you will try 2 here again, and then you will try 3 again, and then again, and then finally you will find the 0 is empty. Then you will fill up bucket 0. So it's going to take a whole lot of time. But if you try to insert the number 0 here, then the bucket index is simply 0 at the first time. So you can simply fill up the bucket index 0, so it's going to be pretty fast. Yeah, so if you catch these timing differences, you can run something about the hash or the key. And so because this is some sort of the binary testing, every time you succeed to catch these timing differences, you can run a 1-bit information at a time. And the question is that is this really doable in JavaScript? So JavaScript is running on top of browsers, and then there is JavaScript engines. And then it is also possible that there is a JIT engine. So there is, so this language is too high level, and under the JavaScript, a lot of things are going on that we don't really understand. So we never know. And especially for the JavaScript, and even the timer is milliseconds. This is not really microsecond or nanosecond. So it is really, the granularity is not really good. But we can simply overcome this challenge by repeating these steps like 1,000 times. Then we can get the reasonable granularity for timers. And so the table size can be really big. So we don't really find the proper buckets. But if we try again and again and again, then we can finally succeed it. So it is all about the calibration to get the right timer. So to further better attack this, so we try to find the weak key. So weak key is a key that the second hash function in the double hash returns as small integer numbers. So because it's linear proving cases, it's going to be pretty simple. But for these double hashing cases, because this mapping between the key and hash are a little bit complicated, so we want to avoid the fuzziness of this double hashing. So that's why we try to find the weak key, which actually returns the small integer numbers. And we haven't really proved this mathematically, but this key can be found with the high probabilities. If you try like 1,000 times, you can always find it. So what we did is that repeat this, simply creating name object again and again and again until we actually find the weak key. So we implemented this as a prototype. And because the WebKit has the different hashing function implementations, like string hash or something, so we ported the C++ implementation to the JavaScript, because our tag is written in JavaScript. And we also pre-built the inversion table. So usually, if you use the simple hash functions, so you do the hash from bucket. Oh, I think I flipped this around. Yeah. So the hash function inverts to the bucket, and then it will return to the string and number. So usually, hash function is taking the string or number, then it will return the bucket. So we built up the pre-built inversion table so that we can further optimize our computations in the JavaScript. So we are currently looking at 12-bit, and it is also possible, theoretically, it is possible up to lick the 23 bits. So because we don't really have the nice mathematical properties to find the weak key, so if this table size is too big, then we cannot really find the weak key. And sometimes we cannot really verify that this is actually a weak key or not. Yeah, so to actually show how this attack is working, we inserted one additional line. So you can see this WTF log always, and then printing out the address. So you can see this hash is actually the address. So yeah, let me show you the demo. So let me first run the Safari. Oh yeah. So let me visit the data leaking page. So the top graph shows that the calibration. So x-axis on this graph is the chain length, I mean the number of the collisions, and the y-axis shows the time. So what this actually shows is that we can actually catch the timing differences. If there is small number of the collisions, then the searching time is pretty small. I mean, it is pretty fast. And if there is a whole lot of the collisions in the hash table searching, then the searching time is pretty long. So if we succeed this calibration, we finally try to infer the key. Oh, I think I need to click yes. Okay, whatever. So this shows that how this attack succeeds. So in these cases, please forget about this legend, but this x-axis is actually bucket index. So starting from 0 to bucket index 2 to the 12. In this case, it is 12-bit. So what this means that we first filled up whole tables, like 2 to 12. It is not actually a whole table. We only filled up the half because the hash table implementation, if you fill up the more than half of the table, then it will automatically increase the underlying table size. So we only filled up the half. But anyway, so you can simply think that the table is fully filled up. And then what we did is that we removed one of the slots, only a single slot. Like what it says is that if I remove the bucket number 0, then the searching time will be something like this. And if I remove the bucket number 1, then the searching number will be something like this. And if I remove this bucket, then the searching time will be something like this. So what this essentially means that using this weak key, if you try to search it, and if it is taking the minimum time, then it is possible, and there is high chances that this bucket index is exactly the first return value of the hash function from that bucket searching algorithms. So let me run this algorithm again. so that how it is actually printing out. So because the computation takes time, and also sometimes it can fail, so you will see that this succeeded at the first time. So you can see the value 450. So this is LSB of the address space, and if I go back here, it is 450. So it is like 100%. This is like because the number of the bits are pretty small, so it is like 100% attack. It's pretty reliable. And let me show you how this also fails, because I spent a lot of time to make this work. Yeah, so it is trying, and sometimes it is failing. That this case is always success. Okay, let me just show you. Yes, so the attack is working something like this, and we reported this vulnerability to WebKit, and it is patched, and that is also let it work. So if you follow up this hash table attacks, and most of the attacks were about the DOS attacks, like the hash function algorithms are deterministic. So you know how the hash table is filled up, and you can always trigger the worst cases. So if you can always trigger the worst cases, it is directly turned into the DOS attacks. And also in the Firefox side, and there is similar attacks on hash tables as well. So how we actually stop these attacks? So the first cause of this attack is that the hash function is always deterministic for controllable object. And controllable object means a string object or number object. Yeah, so you can think that, why not? We always need deterministic hashing for this because it must be fast. So like if you have used some simple hash functions like integer hash, and that is always deterministic. If you give the same key, the return value must be always the same. But sometimes this is not really good or secure. So crypto people have thought about how to actually implement the universal hashing. So universal hashing means that every time you load up the application or you start up the application, then there is some seeding value. Then that seeding value makes the hash mapping whole different from the previous run. So the other countermeasure can be that you can simply not using the addresses. So the first one is that you can simply use the random values. So instead of using the memory addresses, absolutely you can use the random addresses. But it is not really, this is pretty low chances, but still it is possible that there can be the collision because the address, the space of the key is not really big like the cryptos. Like crypto is talking about like 2 to the 128 or 2 to 256, but here we are talking about 2 to the 32 or 2 to the 16. So XOR masking can be also the solution. So this is actually the design choice of PHP. And, but the problem is that there can be the two-time pass. Let me show you the example code of the PHP. So this is how PHP is computing the hash for certain object. So this routine shows that how you initializing the random masking. So it is simply getting some random value from some random generator. And then once you get this masking value, then at the next time, you simply do the simple XOR onto the same key. And if you know about this one-time pad, and one-time pad only guarantees the security that the key is never reused. So that is the whole assumption of the one-time pad. And if you break that assumption, then you never know the security of these hash functions or using the one-time pad or two-time pad. And so two-time pad means that if you use the same key for this XOR masking or XOR operations, then you cannot really guarantee the security of this guy. So what this guy is essentially doing is that using this masking value over again and again. So the simple attack on this can be that you just get the two different values, then masking it, and then XOR together. Then you can get rid of the masking value, because it is XOR, and if you XOR the same value, then the random factor will be gone. So let me switch the gear to the Android part. So Android ASLR is about the, so people may wonder why ASLR on Android, because Android applications are written in Java, so is there any system attacks? But right now, the trend is that a lot of apps are written with the native code, and Android team also want to prevent the exploitation from that native code. And it is adopted incrementally. As I mentioned before, ASLR increased the overhead, performance overheads. So especially for the early Android devices, which has small memory and the limited computing power, CPU, so there was performance concerns. So, and then to implement ASLR, you need to enable the PIE, position independent executable. But if you turn on this PIE, there is low latencies, and also there can be the memory overheads. And finally, Android 4.1 set to implement the full ASLR enforcement. So let me see the, how this ASLR enforcement is actually implemented in the Android with the, and it is related to the performance prioritized design. So Android is essentially the multi-layered architecture. So Android applications run on top of the direct VM, DVM. And then when it is running the application, it also loads up a lot different runtime libraries. And because if you simply do this sort of the steps, like on top of every time you execute the application, you initialize the direct VM, and then you initialize the Android runtime library, and then run the application, it's going to take a lot of time. So you really want to avoid doing this. So what Android team comes up with that is called Zygote. And Zygote is the process creation module. So here's the Zygote process with the template process of hosting apps. So in this Zygote process, you have the already initialized direct VM, and also you have already initialized Android runtime library. And then every time you want to create the application, you simply do the fork. Then you will have two different instances, though it is identical. Then you execute the application on top of it. And then if you want to create another application, then fork it again, and then execute the application again. So this is going to be really fast. So first, fork is fast. And even if it is identical, there is copy on write. So every time you change some different steps, changes something in direct VM, changes something, even in identical part. So that will be automatically deduped. But the problem is that because these are doing simply fork, they share the memory addresses. So if you think that if you really do the reinitialization again and again, then because of the ASLR and PIE, the memory addresses for these modules will be always different. But because this guy is simply doing fork, so the memory addresses are always the same for these modules. So let me talk a little bit more about how this is working in internal. So that is Zygote. So Zygote is something like daemon in Android, and the AM is activity manager. So first, AM requests to Zygote. If the user click the icon on the Android, then to create the application, then AM is sending the request to the Zygote, saying that the user wants to create a new application. And then Zygote is forked. And then, so let's say this is the browser, and then you load up the browser by specializing it. So specializing means that you load the specific application. But because this is forking, so every single module layout are just the same. And these were all the shared libraries. So all applications have the same memory layouts if we are relying on the Zygote. And we say this weakens the Android ASLR security. So before we talk about how this can be attacked, we got to think about what's really the hurdle or challenges to build up the fully working exploits. So if you want to make up the fully working exploit, so in the current settings or in current hard models, you need to exploit the information leak vulnerability first. And next step is that given the ASLR information from the information leak vulnerability, you further exploit a control flow hijack vulnerabilities like use after free or heap overflow, something like that. And these two different attacks should be achieved in the same application if it is ideal. But because address information is shared across different applications, so we can do follows. The first attack is remote coordinated attacks. So what we are going to do is that we're going to merge up two different vulnerabilities. So we're going to attack the information leak vulnerability in the Chrome, and then we attack the control flow hijack vulnerability in the VLC, that is media player. And then if we do merge up, then the ASLR information from the Chrome side is still valid for VLC side, in VLC side. So yes, we can reduce the vulnerability searching spaces in this case. And we can also do the local Trojan attacks. So if the user simply installs some simple application, then this simple application can always void out the ASLR because it can simply run the native code, and that native code can discover whole memory layouts and then send it over. So here's how the remote coordinated attack is actually working. So in this diagram, we assume that the victim is running the Chrome, and the attacker is running the web server, and further assume that the victim visited attacker's web server. Then attacker's web server is going to serve the malicious JavaScript file, and this malicious JavaScript file going to exploit the information leak vulnerability. And after that, using the same JavaScript file, we're going to send the memory layout information, send back the memory layout information to the attacker's web server. And then using the URI intent from the JavaScript, this is simply open function in JavaScript. And if you specify target URI with the specific application's intent, registered intent, then you can automatically launch the VLC player with the specific file, specific URL. So what this VLC player is going to do is that once it gets the URI intent, it will automatically contact the attacker server and then start to download the video file. And inside of the video file, because we already know the ASLR information, we build up the ROP gadgets with this already known ASLR information. So local Trojan attack is that we are assuming that the user is installing the zero permission the Trojan apps. So this is going to ask almost no permissions. And then this is going to scan the whole memory spaces using the native code. And then layout information can be further exported, like using some URI intent, and you can also, then you can send it back, send to some other application, or simply, if you have network permission, then you can send it back to some other remote servers. And once this Trojan app is installed, then ASLR can be simply bypassed because you already got the whole information. And that whole information is going to be valid for as long as the device is rebooted. So we actually wrote up the paper about how we can actually stop this, and which is published in the IEEE Security and Privacy. And please take a look if you have a chance. And these are the references. And thank you very much for your attention, and I'm happy to take any questions.